I'm Janie Schwab, the director at Dudley Observatory, and I'm really happy to welcome you all here tonight. I want to thank so many of you for supporting us, for helping to sponsor the lectures, and thank you for being here tonight. It's my pleasure to introduce Dr. Anna Frebel. Dr. Frebel is currently a Clay Fellow at Harvard University, where she works at the Center for Astrophysics in the Optical and Infrared Division, and she's also affiliated with the Institute for Theory and Computation of the Theoretical Astrophysics Division. Her research interests broadly cover how the oldest stars can be used to learn about the very first stars. She did her undergraduate studies at the University of Freiburg in Germany. In 2006, she completed her PhD thesis at the Mount Stromlo Observatory of the Australian National University in Canberra, Australia. And yes, she was there when they had the fire. Following that, she was the W.J. McDonald Postdoctoral Fellow of the McDonald Observatory and Department of Astronomy at the University of Texas at Austin. She's written 25 articles in peer-reviewed journals, as well as a number of articles for popular science journals. And she now has a book deal to come out with a basic popular level astronomy book. She's won numerous awards, and among them were the 2009 Ludwig Biermann Young Astronomer Award of the German Astronomical Society, and then this year, the 2010 Annie Jump Cannon Award in Astronomy for Outstanding Research and Promise for Future Research by a postdoctoral woman researcher. So, in addition to that, she apparently makes a mean cupcake. And if you look at her website, you'll see photographs of different observatories and their rendition done in cupcakes next to it. So when we go to build our new observatory, I know who I'm going to ask to do the design. So please welcome Dr. Anna Frebel, speaking on our cosmic ancestors, the oldest stars in the universe.
Thank you very much, Janie. Well, thank you all for coming, despite the bad weather. It's also bad in Cambridge, so I think fall is coming. So today I would like to talk to you about the oldest stars. Well, we all live in a wonderful galaxy here, and or like one of those that's pictured up there. And I will walk you through all sorts of things that you need to learn and understand in this next hour in order to really appreciate what the oldest stars are like and what they tell us about ourselves. So brace yourself. I welcome you to a little cosmic roller coaster ride with me. But I hope it's going to be good fun. So astronomy is not just looking at the stars or galaxies. It comprises all sorts of different topics. And especially here, there's a connection, a very close connection between what we call nuclear astrophysics. And you see an illustration of an atomic nucleus there. Then there is stellar astronomy in the middle. You see that is a picture of a supernova explosion, so it looks rather pretty, but obviously it's made from elements, from nuclei, shown to the right there. And then overall, we have cosmology, so if you put it all together, all the stars and all the galaxy, you make up the entire universe, and when we study that, we call that cosmology. So there's a strong connection between the tiniest things, these individual nuclei, and the whole of the universe itself. And it's all combined in stellar astronomy. But before I tell you more about that, let's talk a little bit about the elements around us. So there is oxygen and nitrogen in the air. I hope you're all familiar with that and keep breathing. Then there is carbon in all sorts of plant and human material. We have hydrogen in the water. There's more carbon in, my hand, my body, all of you. Well, then we have calcium in our teeth. They're also good to have. And so is blood. That's made of iron. And finally, we have things like diamonds. well, that's all carbon in the end. And the rest of the ring is made from silver or gold. So these are all chemical elements that we see around us every day. And as I will explain to you in the next little while, is that they have all come from stars. So here is the periodic table of the elements. I hope at least in high school you've all seen that once. It's okay if you don't remember all the details. What's important is that, well, there are lots of elements out there. We can study them all in stars, and they have all come from stars. But because this is really a complicated diagram, I will show you, first I will show you that this is not my work, I promise. But some other people are really excited about the periodic table of the elements, and it seems that this is not complicated enough, so they turn it into baking. So these are 118 cupcakes lined up according to the periodic table of the elements, apparently for a 7-year-old birthday, science-themed birthday party. So I encourage you to do that, for your children or grandchildren next time for the next birthday. But yeah, this is really complicated, and astronomers, life is tough, and we want to keep things simple. So this is, the astronomer's periodic table. Before, you've seen the chemist kind of version, but this is the astronomer's version. So there is hydrogen in the universe, 75%, and there's helium in the universe, 25%. And well, if you sort of add that makes already 100%, but you see the squiggles, and it's actually less than 1% is together in all the other elements. Okay, so to keep life simple, astronomers just call all the other elements, it's not really fair, but they do it anyway, they call all the other elements metals. Again, it's not the chemist's point of view, it's just we want to keep life simple. So, of course, you can imagine that, these metals, if you group them all together, well, I said it's not really fair, and there's a lot of information that gets swept under the rug there. So I will, give you some more details on a few of those metals. So let's recap first a few things. So what's a star made of? The sun is our pet star, so it shines and gives us light every day. That's a good thing. And the sun is made of 75% hydrogen, 25% helium, and then there's this tiny, tiny fraction of metals, as what I just showed you before. But the question really is, why does the star shine? Where's the light coming from that makes the sun shine? And so now we have to go through some more complicated things here. That's called nucleosynthesis. And that explains how the elements actually are created. So if you take to the left, if you start with just 4 protons, these are just atomic particles. Doesn't really matter what they are in the end. If you bang them together, you make a new element. It's called helium. That's pretty easy. If you bang together 3 helium atoms, these ones in the middle here, you make a bigger nucleus, and that's carbon. And then if you jam another helium into the carbon, you make oxygen. So, and this is how it goes throughout the periodic table. You just bang and put more things together, and this is how you make bigger atoms. Now the trick hereby is that when you bang together all these elements here, the protons and the neutrons, there's actually, these ones weigh a certain amount. If you put them together, well, you can make the math. If you just add a proton mass and a neutron mass, you get this one. Right? So that's very simple math. The number's actually not very important, but just look at this number here. And then people have gone out and measured the mass of a helium atom, which is this thing here. And this number is slightly different. And that means that some tiny, tiny fraction of mass is actually transformed into energy. And this is why the sun shines. This is why we have day every day, because of this, it's called mass defect. Thanks to Mr. Einstein here. That's the very famous equation, E equals E since C squared. Okay, just if you do the math like this, you arrive at something else, and when you measure what's actually there. So I think that's pretty neat. Now we know why the sun shines. Any star, actually. So I hope you're all active stargazers. Sometimes a little bit difficult in the city, but if you go out, especially in the winter, on a clear winter night, you will see the constellation Orion. I hope you have seen them all. There are two illustrations of the same thing. One is, really just taken in the city, and this is more sort of from space. To make it a little bit easier, I've drawn a few lines in here. So this is the belt of Orion. Here's the sword. Here are the two legs. And then here we have two shoulders and some kind of head. You have to be a little imaginative, but I'm pretty sure you'll manage. So why am I telling you this? Look at this guy here. This star has a different color than the other ones. It's not blue, but it's sort of yellow orangey. And what's happening in that star is that this star is currently fusing elements. It's currently making carbon and oxygen. Exactly what I showed you before on that cartoon. So here we have a star that's actively burning and creating these elements. And all the carbon that is in our bodies comes from stars like this one. That's a red giant. You could have guessed where the name is coming from the color. So next time and this constellation is going to be up in a few months again in the winter. Next time you go stargazing, please check out this little carbon burner up there. So it's the left shoulder star. And remember where you come from. So then, the cartoon stopped sort of at oxygen, but you've seen before the periodic table doesn't stop at oxygen. You have to create more elements, and that happens during the star's lifetime. And towards the end of the lifetime of a star, the guys look kind of like this, sort of like a big onion shell. And in the middle, you have, let's start from the outside. Here you have the hydrogen, and then you have the next heavy element, the helium, and then you have the carbon and the oxygen, and then neon and magnesium and silicon and iron. So in the end, so it can make all these different elements, one heavier after another, and it just kind of starts to layer itself like that. And then something terrible happens. You can only get light energy out of the star's nuclear fusion until you reach iron. Iron is the dead end. So the heaviest element a star can make during its lifetime is iron. And because it doesn't go any further, but the star wants to get hotter and hotter and wants to make more, the whole thing explodes. And that's called a supernova explosion. And here is already a schematic of what all sorts of elements pop out of such a supernova explosion. And here's an artist's impression of how a supernova explosion might look like. This is the most energetic event in the cosmos. And in this very, very short explosion, the conditions are so extreme that suddenly all sorts of crazy things are going on, and suddenly, only then, in that short amount of time, you can make all the elements in the bottom half of the periodic table. So all that complicated stuff from high school that was always too complicated, even for me when I went to high school, all made in these supernova explosion because it's such a dramatic event. So, in summary, all the elements we are made of, they come from stars. And I have a list there, but I also brought you this little box here. And there are lots of things around you that remind you every day that we're all children of the stars. So I have a water bottle here, hydrogen and oxygen, salt, sodium and chloride, toothpaste, fluoride, matches, phosphorus, straight from big red giants. You've seen them in Orion. You can see it right now. Now, obviously, the phosphorus from these matches were not made in the star right now, but some time ago. Let's see what else I have. I like to drink a shot every now and then. That would be carbon, but the glass is silicon. I have a few coins here, one left over from my time in Australia, copper. All from a red giant star or from a supernova explosion. Sometimes I paint this color, contains cadmium, really exotic element, comes straight out of one of those supernova explosions. So I'm very happy to pass this around if you want to look at it, or you can come later. So it's all star stuff. So you will now understand why I called my title, the cosmic ancestors, because we're just part of it. We're part of this ginormous cycle of making elements, recycling elements, reusing them. And, it doesn't feel so bad. I feel pretty good being star stuff. Okay, so now we learned all the hard part now, the nitty-gritty bits. Now we need to put this into context. So a very long time ago, there was the Big Bang. We think it was about 14 billion years ago, right here. And then a few 100 million years later, the very first stars emerged from this pristine material. So in the Big Bang, or after the Big Bang, I should say, there was only hydrogen and helium in the universe, no metals. The universe liked it simple back then too. So the first stars formed, and they exploded as supernova explosions. And whatever these stars had cooked in their life, and plus whatever happened in the supernova, got ejected into the interstellar medium, and it polluted the universe forever. Tough luck. And you can then, you already know, I guess, what I'm going to say. Then there were, more generations of stars, and they produced more metals, more elements, and polluted even worse. It's really bad. And it got that far that at some point, well, there were the first planets also, but you need quite a few, large amounts of carbon and other iron metals to make planets. So that sort of happened somewhere around here. And then, well, today, yes, we're quite happy with all the elements we know and love. So, well, with these old stars, we can look back in time, and we can push by finding older and older stars that are born in this sort of region here, this regime, in the early universe. So very close to the Big Bang. This is not to scale. Close to the first stars. We cannot quite reach the first stars for a number of reasons, but we think we can push as far as the second and all the early generations. And that was at a time when the universe did not contain many heavy elements, because they had to be cooked up in all these supernovae. And here's a cartoon of how we think chemical evolution proceeded. Imagine that this is the Big Bang, pristine hydrogen-helium cloud. You make little stars, they grow up, make all this carbon, then they explode as supernova, and all this material that's produced gets put back into this reservoir here, and then it starts again and again and again. And so the metal content over the course of the universe went up and up and up and up. There's no way you can take away metals. There's no cosmic vacuum cleaner. It's going to get more and more chaotic, and there will be more and more elements. So we are looking for the stars with the least amounts of heavy elements in them when we want to find the oldest stars in the universe. Okay? Because the chemistry tells us about the age, because we can never take away metals. So the more metals there are in a star, because it formed from that material, the younger it has to be. And in return, if we look for the ones that have hardly any iron, they must have formed very early on in the universe. Now, for some of you might have some prior astronomy knowledge. Here's a little blip for you. So all these old stars, they reside in the halo, and I'll talk later about what the halo means. They're called population 2. The sun is a young star. It's called population 1. And then there are these very first stars, the ones that form just from hydrogen and helium, and they're kind of special. So they're called population 3. So here is a sort of cartoon picture that I put together to illustrate the chemical evolution of the universe. So there were these first supernovae, and the color sort of represents the degree of pollution, of enrichment. And there were more and more going off, and then the stuff gets sort of dispersed into the interstellar medium, into the gas that's simply around. And then new generations of stars form and produce more metals, and you see the color gets darker and darker, so there are more and more metals in the universe. So you see all sorts of things pop out. Here's something. So these are a whole bunch of supernovae that explode and produce these metals, and you see here how it gets dispersed into the surrounding. I'll just run it again. So this is kind of the real deal. Okay, again. Well, I just go back. Let's try it again. Yeah. So still a little bit bright here, but you can see every now and then there's something here. Something popped up, and you see it turned a little yellow. So there were new elements produced, and because it was already red before, it sort of got diluted fairly quickly, but it's still quite metal rich. And then there was one at the edge here that produced new metals. So this is what we do as astronomers. We don't, sometimes we make cartoons, but we also have to do it the real way. Well, this is all fine and dandy. Now let's just kind of speed up cosmic chemical evolution. You've seen this sort of time cone before. And let's go to today and see where we actually are with respect to the universe. So, well, I hope you all know that we live on a planet called Earth in a solar system, and we're all going around the sun together with all the other planets shown here. And we live in the outskirts of our home galaxy, which is called the Milky Way. We live quite a bit far off the center of the Milky Way, but that's good because there's a big black hole lurking, and we wouldn't want to get any close to that anytime soon. So I think we have a pretty good place way out there. And in terms of scales, if you imagine that the Milky Way here has the size of a soccer field. I'm from Germany, so I have to show you a soccer field rather than baseball field or something. And then we, the solar system, we're kind of like a tiny little needle in the soccer field. So the Milky Way is a big place, but it gets even bigger. Well, this is a face-on image of a galaxy that is, of course, not the Milky Way, because we can't zoom out and look. You can only see yourself when you look in the mirror. We can't really do that with a galaxy, but this is how we imagine the Milky Way would look like if we could fly out really far away and then take a picture of it. And so that's the face-on view, and the edge-on view is such. So again, here's the center with a big black hole. Here's us, and this is the galactic disk here, and there are all these young stars like the sun, these population 1 stars I mentioned before, they're located there. And then what I circle in here is called the galactic halo, which still is part of the galaxy, but there are so much fewer stars there that you can hardly see it. And that's called the halo of the Milky Way. And this is the home of the oldest stars, because the oldest stars in the universe, they're really poor guys. They got left over from all sorts of processes, and they're now located sort of down here and up here. So if we're interested in finding out about the oldest stars, that's the place where we have to look. There are probably also some in here, but there are so many metal-rich stars that it's kind of difficult to find them there. Before we go on, we should talk a little bit about stellar lifetimes. So I said, well, old stars are old. Well, fine. But it's actually not that simple. So the age of a star depends on its mass. It's different than with people. Short people and tall people have roughly the same lifespan, but with stars, it's not like that. So little stars, smaller than the sun, in good googly fashion, they live very long. Okay? Some can, the smallest ones, they can live up to 100 billion years. Now that's a number even I can't comprehend. Okay? If you can't, that's fine. It's very, very long. So most of the stars are smaller than the sun, so I call them the good citizens, right? They get the eco-friendly stamp. They're really fuel efficient. They burn very, very slowly, so they can live for that long. Then there are many stars that are a few times bigger than the sun, and they live much less long. Perhaps 1 billion years, perhaps a little bit less, perhaps a little bit more. Well, we know the universe is something like 14 billion years, so yeah, you can have a few stars in the lifespan of the universe. So, well, but still these guys have, fairly large carbon footprint, I would say. And then there are the guys that are much bigger than the sun, 10 times, 20 times, 50 times bigger than the sun. They're really big guys, and they're having a lot of fun, so, but they die rather fast. So they're the real bad burners here. They're not so eco-friendly. But these are also the guys that give us the new elements fairly fast, because they, for sure, explode as supernova explosions. So they're actually important. So now finally we come to the oldest stars. We've put together all sorts of little pieces in order to understand chemical evolution and how we make elements and where we're located in our galaxy. Now, why should we really care about old stars? In parts I have answered that, but I would like to kind of summarize that. So, well, to recap the previous slide, these stars have to be very small, because if they need to have very long lifetimes, so we can still observe them today. So we know that they're all smaller than the sun. Okay? They're still shining up there. If you have a telescope, you can observe them. You can take pictures of them, or you can just look at them. Some look a little bit redder, some look a little bluer. That depends on the type of star. So, and we can then go on and analyze these stars in detail, and you now understand why that's interesting, because we can look back in time and we can find out how the universe looked like back at this early stage when there were not many metals in the universe. So I often refer to this sort of work as stellar archaeology. We're looking back in time with some fossil records. Now here I have a picture of some actual archaeologists digging in the dirt, trying to find some bones. Well, I don't really dig in the dirt, but I search the sky for the oldest stars to then learn about the early universe. That's probably a big red giant, probably far away because it's less. It appears less big, but that's just the distance and the projection effect. Well, to be honest, I have absolutely no clue. But I know there are lots of stars, and some of them must be pretty old. Because if you look through a lot of stars, you will find an old one eventually. But you will understand this slide now, because my work resembles finding the needle in the haystack. And the haystack are all these young stars, all these sun-like stars that are all nice. They're wonderful stars, but they're not the ones I want. Okay? So I have to find the needle in the haystack. And you can, of course, imagine that the stars left over from the Big Bang are really quite rare. Okay? And to give you some rough estimate, so we have about 200 to 400 billion stars in the Milky Way galaxy. Stars as old as the universe? Any guesses?
0.
Well, complete, yes. Make that almost as old as the universe. Well, I just guessed myself because we don't really know, but it might be something like 50 to 5,000 or something. Your guess would be as good as mine. The important thing is that we have to find out, because we can learn all these things about this early time. So the way we do this is, we need to learn about the chemical composition of the star if we want to study the elements. And we do that with spectral analysis. Okay? So you can take pictures of a star, and that looks pretty, but it's actually not telling you anything about what the star is made of. You need a different technique for that, and we call that spectroscopy. And the way you can imagine is that, well, here you have a star. You need to find out what it's made of. You need, some examiner, and then we take spectroscopy. And, well, the big question really is, what on earth is spectroscopy? Well, that means we split up the light, we stretch it, and suddenly we start seeing things. That's very mysterious. But the way it works is roughly illustrated here. I hope you can see that. So, imagine the cheese is your light and your spectrum coming from a star. And then each element is something like this little intruder here. And the intruder eats away stuff at certain positions, certain locations throughout the spectrum. So at different locations in my spectrum, which means different wavelength. Okay? Light has different wavelengths, and it eats away light. Well, you'd say, ooh, that's not so good, but it's actually really nice, because each element eats away at different wavelengths, at different locations in the cheese, and sometimes, and we also know whether the light, the element is going to produce a small chunk, it's going to eat up a small chunk or a big chunk. Okay, I kind of paraphrase it here. Different mice eat at different locations, and sometimes they're really hungry, and sometimes they're just snack. Okay, so all the elements do that, and we know this from atomic physicists, what each element eats and where. And so this is how we can identify in a spectrum what element is wiggling around in the star. And I will show you some examples now. So a spectrograph, which is the tool that we need in order to do so, is a prism, for example. You've probably seen all that, and it splits the light into a rainbow. This is what's shown here, solar spectrum. And then all the different elements eat away, you see the dark lines here, light at different positions. You all know this one. These are the sodium D lines. Have you ever seen an orange streetlight? That's sodium eating away in the yellow part of the spectrum. You can reverse the process so it doesn't eat away yellow light, but it emits it. It lights in this color. So that's sodium. So and here you see the spectrum. Well, hydrogen, these are all hydrogen lines here. They eat away a lot at these characteristic wavelengths here. And then there's, for example, calcium eats away less at this particular wavelength. So what we do every day is we measure these line strength. We just see how much area is this, if this is a big line or if it's a small line. And then we stuff it into the computer, do some magic, and then out pops the chemical composition of the star. But it's not quite that easy, of course. We need a big telescope for that. And I have, for example, used the 8-meter Japanese Subaru telescope on Hawaii. It's located on the Mauna Kea mountain on the Big Island. If you ever go there, I think you can even tour the summit. Here's a picture of the summit with a few telescopes in the background. They come in all sorts of shapes and sizes. These are the Keck telescopes. You might have heard about those. This is the Subaru telescope. That's me and my Japanese collaborators here with a hard helmet. That was fun. You don't really need a hard helmet to observe, though. Don't get me wrong. We made a tour of the actual telescope and the procedures that we have to wear a hard helmet. But what we do is we sit there all night long in the control room with all these monitors here. You see my colleagues again being more or less pleased with the results. And we just sit behind a lot of screens and press a few buttons every now and then and inspect the data we are taking. So no hard helmets. Okay, well, so this telescope helped us, or that was the one telescope that with which we discovered this star here. So this is the most iron-poor star that we know. Perhaps not quite in the universe, but the most iron-poor star we know. Now, I'm not going to ask you later to remember these telephone numbers, but this HE doesn't mean he or anything crazy like that. It just means that these stars were discovered in the Hamburg ESO survey, and that's short for HE. So, yes, well, so these are different types of stars. Here are the temperatures listed. It's actually, these are not very hot stars in the grand scheme of things, but 6,000 degrees, I wouldn't want to stick my finger in that. So you can see also that this one here is a bit redder than this one, and this is indeed a red giant, and this is not yet a red giant, but it's going to become a red giant in its next life phase. These numbers aren't really important either to you, but you just have to trust me that the smaller the number here, the better it is when you want to find the most metal-poor stars. So -5 just means it's less than 5 orders of magnitude less than what is in the sun. And we talked about it before. The sun has 1% of all the elements together. Take out the iron, just one element, much less, and then we have many, many, many times less iron than that. But I will give you another example that illustrates what this number actually means much better. Before I do that, I should show you some more spectra. I have not so many pretty pictures. I have to apologize for that, but I am a spectroscopist, so you just have to bear with me and understand that each element absorbs at a certain wavelength, and it produces these lines that we can measure. So here is the spectrum of the sun, and there are so many lines here, I can't even label them all. And it's a lot of work if you work on this. It's awful. It will take me forever to analyze every single wiggle here and to try to measure how much space is there. I'm a good astronomer. I like to keep my life simple. I told you about the astronomer's periodic table before. That's why I work on metal-poor stars, because the spectrum of really, really metal-poor star, you see only 3 lines left. Oh, I can finish work at noon. I don't need to stay all day long. It's only 3 lines. Well, and this is our most iron-poor friend. You can see what happened to that line here. It's almost vanished. There's so little in this star that there's hardly enough power to make an absorption line, this line anymore. You might think, oh, there's nothing left to measure. Well, yeah, that's true, but we want to find these stars with just these tiny, tiny lines that make our life easy for measuring them, but it makes them really complicated when we want to find out where on Earth these stars are coming from and what made the iron in this star. This is a very old star, and perhaps only one supernova in the universe was responsible for the iron in this star. Right? The star formed from an enriched gas cloud early on that possibly was enriched by just one star, one supernova. So, here we go. So, just to recap that, here is a star that we call extremely metal-poor, and you see there are quite some chunky lines here, and then here's the hyper-metal-poor star, HE 13, 27, 23, 26, and there's hardly anything left here anymore. And I calculated here, for your amusement, that for each iron atom in this star, there are 800 million, I guess, well, it's a very large number, hydrogen atoms. Okay, so in the sun, for every iron atom, you have 31,000. So, that's sort of the size of a small town. So one person in a small town would be the iron, and everyone else would be hydrogen. That's the sun. And then you go to a really, really big city, Tokyo or something, or half of Japan, and then only one person would be the iron, and everyone else would be hydrogen. That's not a lot. In fact, if I just calculate how much iron mass is in the star, and I should first say that the star is some 300 1,000 times bigger than the Earth. There is 100 times less iron in this star than we have in the Earth's iron core. Okay? Not a lot. So if you want to make planets and things like that, you need a lot more iron than what's in that star, because we couldn't even, this star couldn't even make the iron core. And then there are some more scales here. We have more iron in this star than what is believed to be in the core of the moon, but we're not even making it up to Mercury with that guy. So not a lot of iron. That means this star must have formed very, very early on in the universe, perhaps when there was just one population 3, one first star, one first supernova, exploding enriching the universe with iron and other metals for the very first time. And well, we know today that these first stars, they were much more massive, and you've learned by now that massive stars have a fun life, but it's rather short, and so they die quickly, and so we cannot observe them directly anymore today. But we can observe these little guys here, and we can trace back by their chemical composition, we can guesstimate what this guy here must have ejected in terms of metals, how much, which ones, all of that. And this is how we look back in time even more in this indirect way with the chemistry. So let me go on and talk a little bit about a slightly different star. This one is only extremely metal poor, so it's not hyper metal poor like the other ones. But this one is really interesting. It's a bright star. Here's a picture of it. A Greek amateur astronomer sent me this picture. He was very excited that he was able, with his backyard telescope, to obtain a picture of the star. And it's a really old star, of course. I'm working on the older stars after all. And it turns out that in a small fraction of all these metal poor stars, we find what we call the chemical fingerprint, similar to the cartoon I just showed you, of this previous supernova. But it's a different fingerprint than what we've seen before in this hyper metal poor star. And so we think that we see the signature of a very special supernova explosion. One of those that makes all the elements in the bottom half of the periodic table. And you might not have seen this, but at the very bottom of the periodic table, there are the radioactive elements, thorium and uranium. So they're decaying, and that means that there's something ticking in the star. And whatever ticks is a clock. So for the first time today, I can tell you what the actual age of an old star is. Now, you have to wait a few more slides. You're not off the hook right now, but before I could not tell you how old the oldest stars actually are. But with this special star, we can do that. So, first of all, you need to sit through some theory with me again. Radioactive decay. Well, there are two types of decay processes. There's the alpha decay. You just have a big nucleus, for example, the thorium here, and it just at some point says, oh, thorium, I feel a little icky. I just eject a helium nucleus. Okay? Let's just get rid of that. Ew. That's what happens. And then you have a new element plus the helium, and the helium just goes away. Okay, so that decayed. And then we have the beta decay here, where you have the carbon, for example, and the carbon gets really, really itchy, so it scratches a lot. And suddenly what happens is a proton turns, let's see, yeah, a neutron. You see here's a red and a blue, and here's a red and a red. So one of the neutrons turns into a proton. That works. You also get a little a light flash, but it makes a new element, namely nitrogen. Okay, so the number of nuclei particles here is preserved, but because it itched so much, it suddenly has a different, it has more red ones here now than blue ones. Okay, that's how the decay works. That's also a method actually of making new elements also. So that's quite neat. And you don't really need to do anything except for wait. And so the characteristic thing here is called the half-life. You just wait, you just measure the time that you, until the material has decreased by half. And so we know that from the lab, again. So if we find thorium in a star, we can then use this knowledge to trace back to when the thorium was produced and then measure the age. Now this is really like the radiocarbon dating, and some of you might be familiar with that. So in the real archaeology, not the stellar archaeology, you have some kind of old tree or something, or some bones, and you want to date them. And well, you measure how much is left. In this case, it's this carbon-14 to carbon-12 ratio. The carbon-14, as you just seen in the cartoon, the carbon-14 decays to nitrogen. We don't really care about nitrogen in this method, just about the carbon. So the carbon-14 goes down and down and down over time. But the carbon-12 does not. And that means that this ratio changes. And we know that in the beginning, there was a certain ratio that's given by the atmosphere. And then you can see how much this ratio changed. And bang, you have the age for your dead tree. So there's, of course, a small problem in stellar archaeology. Here we know the initial value because the atmosphere is still the atmosphere. We're breathing, and back then the tree was breathing. So that hasn't changed. But in stellar archaeology, we don't know how much thorium was produced in that supernova. Well, that's a bit of a problem. But I have lots of nuclear physics friends and cosmochemist collaborators, and they are really into that sort of stuff. So I go ask them, hey dude, how much did the supernova make? Come tell me. Well, depending on who I ask, I get different answers. There are lots of opinions out there. But well, you have to make the best of it. Here is the stellar archaeology approach displayed. Oh, well, I thought this would look different. Anyway, so here you have, well, these guys who made this plot said, okay, that is the Big Bang. They forgot to put the supernova actually in there that makes the elements, because you have learned by now that the Big Bang does not make uranium. The Big Bang doesn't make thorium or anything else. It makes hydrogen and helium, okay? So we need the supernova in between here, and the supernova makes all these elements, and then the star here, that's the guy we're observing, that forms from this enriched material, and it inherits all these radioactive elements, and then since then, they're just decaying, and then at some point you come along and observe the star, and then you can measure how much thorium and uranium is left in the star. Well, okay, here is she again with her periodic table. Well, I can tell you one thing now. The astronomer's periodic table really is not sufficient to describe these kinds of special stars at all, because in one star we can observe a lot of elements. Well, there's hydrogen in the star. There is helium, but we can't really measure the lines of helium in these cool stars. If you want to know more about that, you can ask me later. But we do have absorption lines from all these light elements. There are more light elements here, magnesium and calcium. You know all of these ones. Then these ones are called iron peak because they're sort of centered around iron. And then here are the special neutron capture elements. So they got produced in these really special supernova explosions. There are more heavier ones. First we had the lighter ones, here the heavier ones, and then here are the radioactive ones. So those are the ones I was just talking about. And then actually from space, you can also observe the ones in green. So this is really quite a good tiling of all these elements that you can study with just one single star. So that's why I call this the cosmic lab. We don't need a lot of stars, we just need the right star, and we can study all of that. And the Hubble Space Telescope is helping me in this endeavor. All these green elements I just showed you, they can only be measured from space. They're not accessible from the ground. The Earth atmosphere shields the absorption, so we can't see them. And the Hubble Space Telescope was actually taking data until about a week ago for this project, for this very star. But then they had some technical problems, and the remaining observations are unfortunately now suspended until March. So I have to wait a little bit longer before I can get to all those crazy elements, but it's going to be good fun. Now, in the meantime, I just introduce you to a few of these really heavy, complicated elements. So, you might have heard of Europe. It's a continent over on the right. Well, an element was named after it, uranium. Here is europium, a very strong absorption line. So this was a very big mouse being very, very hungry. There are other europium lines at other wavelengths, but they are less strong. So this is the biggest one. And then there is dysprosium. Well, this was a small mouse. It wasn't very hungry, but it was actually more hungry at other locations throughout the spectrum. And then here's gadolinium. And so we can see all these so-called rare earth elements in this star. And you really have to learn how to pronounce all these names. They are really complicated. And actually, you know, the internet is a marvelous place. And you can buy all sorts of things on the internet. And I have purchased, well, I'm from Germany, as you probably figured by now, little vial of germanium made in a special type of supernova explosion. Probably in a very old star a long time ago, because it needed to get into the Earth. And you know, the Earth is kind of old. It was probably before then already in the solar system present somewhere, before it made it into the planet. And then in the end, some person harvested it from, I don't know, some mine. And then it made its way to the guy in Austria who has this little internet shop selling me germanium. Now, here's another little vial of europium oxide, straight from this process that made this line there. Could have been the same star. Could have been. And then I have 3 glass beads here with names I have to read off because otherwise I'll mix it up. So here in purple, we have erbium. It's another one of those crazy elements, and you're welcome to look at this later. And then here I have something that's looking green. That's praseodymium. It's a bit of a mouthful. And then finally we have neodymium. Okay? So all made from stars and all available through the internet. Thank God. What would we do without them? So, all right. Here are these elements. But of course, I've been talking about the radioactive ones. And here is the famous thorium line. Now, to give you some more details, the black dots are always the observation. The red line here that connects the dots is my brainchild. I use computer models to imitate the spectrum, and then I compare the two in order to figure out what the line strength is here to get the thorium abundance. And you can see in this case, I've labeled here that the thorium is actually kind of married to an iron line and a neodymium line and a cerium line. Oh, sorry, a nickel line and a cerium line. So they're all smudged together, kind of like the solar spectrum you saw before. And so I have to take this all into account, that these are all put together in order to figure out how much thorium contribution is in this. And to make sure that there's really some thorium, I also made one model where I just threw the thorium out of the equation and said, oh, let's forget about this for now. And this is a blue line. And I hope you all agree that this blue line does not represent all these black dots, okay? So, all good. So we have a nice thorium abundance from this. That's what we need for the age dating. And then here's uranium. Now you might have thought, well, the thorium looks kind of complicated with all these other elements in the equation. Now this is way more complicated. It's this tiny little wiggle here. Here's the blow up. Again, I have played the same game. The top line here is we call this synthetic spectrum, where I just threw the uranium out and said, let's see what happens if I forget about the uranium. And clearly this does not look like the observations. It turns out that this is such a difficult measurement that only 2 other stars have a uranium measurement at all. So these are really special metal poor stars tracing a special nucleosynthesis process that created these elements. And they are really extremely rare. They're the needle of the needles in the haystack. But they are really awesome because we can get an age. Now, I can now tell you what the answer is. If you average all these different, so you can get ages, individual ages for all these element ratios here. Here's our friend thorium to uranium. We like that one best. But you can also use uranium to europium. You can pair them all up in the way you like it. So if you average this all, it comes out to something like 13 billion years. It's pretty old. As I said before, we think the universe is almost 14 billion years old, so that actually works. So this star is almost as old as the universe itself. So, I would like to show you a few more other things now after we talked about the older stars. And I would like to show you a movie, but I have this, somewhere here, because, hang on. Let's do that again. You can see an astronomer's laptop background. It's a bit messy, but here we go. So what I would like to show you now is, I would like to put everything into a little more context. So we learned about the older stars, why we are interested in them, what they can tell us about the early universe. We can learn about the origin of the elements. But that are all only tidbits. And so this movie here shows the so-called cosmic web. It started kind of right after the Big Bang, and you saw just a few sort of branches, little thick knots here. And time is running, so it goes from the Big Bang until today. And this is how we think the universe assembled, how the universe grew. And the older stars formed at that time when the movie started. But of course, we live at the very end of the movie. We live in the Milky Way today, and we observe these stars today in the Milky Way. And the reason why I show you this movie is so you can see that the formation of the Milky Way is a complicated process. And the older stars actually help us to learn about the process that you currently see here. So I should say that this is a dark matter simulation, so our eyes can only see visible light. Well, that's actually a good thing, but unfortunately we can't see what astronomers call dark matter. This is matter that we know to exist, but we can't really see it, and we haven't really detected it, and I could probably give another entire presentation on that, so you just need to accept for now that this is dark matter. But you see all these little we call them halos, little clumps, and those are all proto-galaxies or already real galaxies, and they come together and they form this object here in the middle, or I should say this object here forms itself by eating up little clumps, little galaxies. It's not a nice process actually, it's really cannibalistic. It eats up all these galaxies. And so this is a simulation of something like the Milky Way. And you see it grows from eating up the neighbors. And in the end, you have a Milky Way that's surrounded by all these little galaxies and these little clumps. And it really looks like a big beehive. Now, all I told you today so far was about stars that we find in our Milky Way, in the halo of the Milky Way to be exact. But we can actually also find these old stars in some of these little dwarf galaxies, because in fact we have about 25 little dwarf galaxies that orbit the Milky Way, also in the outer part of the halo, together with all the stars I told you about. Whoop, now I have to zoom quickly. Come on. All right. Ah, you saw something you weren't supposed to see. Well, so here's a summary of this movie, how the Milky Way might have formed. We call this hierarchical growth. But as I said, these are dark matter galaxies, clumps, so we don't really know how many stars they contain. Okay, but for sure, many of them will contain a good fraction of luminous matter, stars and gas and stuff. So something that looks like that. So every one of these little blobs here will have their own first stars, their own supernova explosions, their own star formation. Some halos also interact with each other. It's not just, that the small ones only interact with the big ones. They also interact with each other, bumping into each other all the time. And then, of course, well, there are all these little stars. And you can guess what I like to do. I like to take spectra of them. And I like to find out which of those is more metal poor than the sun, much more metal poor. And so, well, you need obviously telescopes for that. And well, I made this little project. It was inspired by the work on my book. And I did this project together with my student, Julie, from Texas. She came to visit me not too long ago to work with me in Cambridge. And she has a food blog, it turns out. And she wrote the most wonderful comment ever. The only thing that I can think of that's better than an observatory is an edible observatory. So next time you wish you would be able to go to a telescope and see the stars, just make one yourself. It's not that hard. And of course, Janie has taken the punchline out already, but that's okay. We were inspired thinking about science and having ideas. And well, I told you I need a real telescope to observe these stars. Here's the Magellan telescope in Chile that I use all the time, and here's my version of it. So whenever I get lonely or think I need more data, I can now look at this picture. So, but here's the real deal. This is the Magellan Clay Telescope, located near La Serena. It's an hour flight north of Santiago in Chile, in the Atacama Desert. Well, as you can see here, the sky is not always perfect, even in Chile. So don't despair if you have clouds when next time you want to see some stars. You can see here they have more clouds, and they make for beautiful pictures, but of course for observing it's less good. And but it gives you time to enjoy time there. So here's one of the results that we recently published in Nature. We found the most metal poor star in one of these dwarf galaxies. Okay, that we had no idea that these stars existed in these types of dwarf galaxies. And through a lot of work with a bunch of collaborators, we uncovered the most metal poor star in this dwarf galaxy Sculptor. And this is an artist's impression. It is a red giant. It's a carbon-burning machine. Well, again, yeah, this is an artist's impression. Here you see the real data. Again, here's our friend the sun. Just look at this line. Here's a magnesium line, much thinner and weaker than what we have in the sun. So this is very extremely metal poor. And so now I could just start repeating my talk all over again, telling you about all these things that you can do with metal poor stars and that you can learn, but now for a dwarf galaxy. So it's a kind of the Russian doll thing. So don't worry, I will not repeat myself. But you understand now that we can put together the information we have from the dwarf galaxies and the stuff we have learned about the halo, and we can actually compare the chemical composition of the older stars to see whether there are any similarities or any differences. And it turns out that if you believe in this hierarchical merging, which is the current consensus view of galaxy formation, that analogs, so systems similar to the surviving dwarf galaxy, must have had a large contribution to the formation of at least the galactic halo. And that means that the chemical compositions of these stars should be identical, the old ones, not the young ones, but the old ones should be similar because it's kind of the separated twin phenomenon. You had this dwarf galaxy, it deposited its stars into the halo of the Milky Way as it got shredded, and that's what we're observing today as the older stars in the Milky Way. So by looking at the leftovers that haven't been eaten up yet, we might find similarities. And indeed, we have found this. This is very new work, which supports this idea that small dwarf galaxies really do provide all the metal-poor stars in the galactic halo. So that brings me to the end of my talk. Here is some star stuff for you to take home. Well, first of all, I hope you enjoyed learning about stellar archaeology and that you will remember it for some time, and that you remember that we're all made from star stuff. And I think that's a wonderful thing. We're all connected through the stars. And we can carry out spectroscopic light analysis of these objects to learn about the origin of the elements, and more importantly, look back in time to a time when the universe did not contain many heavy elements. And then finally, well, the older stars really are kind of old. They're almost as old as the universe, 13 billion years. And we can find similar objects also in these dwarf galaxies. So I wish you well, and I hope that next time you see the stars, watch out for the big red giants. You'll find them all over the sky, not just in Orion. And with that, I would like to thank you and use the words of the little prince here, who wisely already back then realized that talking about stars for others who are scholars, there are problems. But I really like them, and they're wonderful problems to have. Thank you.